John Horton Conway was a highly charismatic mathematician born in the city of Liverpool, England on December 26, 1937. Somewhat eccentric and with a deep love for games and puzzles, his flashy clothing and long, unkempt hair stood in stark contrast to the usual conservative image of the typical university professor of his time. For him, mathematics was both an art and a game, and although he had achieved extremely high-level mathematical accomplishments, he preferred to talk about games, riddles, tricks, and visual patterns that fascinated him. At Princeton University, one of the most prestigious institutions in the world, he held the John von Neumann chair, ironically named after the very von Neumann who had inspired him so much. Princeton was also home to legendary figures such as Albert Einstein, Kurt Gödel, and of course, von Neumann himself. Fascinated by a problem posed by the great von Neumann, Conway set himself an ambitious goal. Was it possible for a machine to replicate itself, like a living cell does, but within a purely mathematical environment? Von Neumann had already toyed with these ideas, but Conway wanted to take them even further. Conway aimed to create a set of rules as simple as possible that could give rise to complex, unpredictable, and potentially self-replicating behavior. His goal wasn't to create just a game, but to explore a captivating idea, how complexity can emerge from simplicity without a central designer. And from that pursuit, in 1970, his most famous creation was born, the game of life. But the game of life is not a game in the traditional sense, played with dice or cards. In fact, there are no players or a goal to win. It's a simulation, a type of system called a cellular automaton. Sounds technical, but the idea is incredibly simple. Picture an infinite grid like a never-ending chessboard. Each square on that board, called a cell, can only be in one of two states, alive or dead, that is, on or off. From there, the system progresses in steps or turns. To determine what happens in the next turn, three very simple rules are applied to each cell, based on the state of its 8 neighboring cells. A live cell with fewer than 2 live neighbors dies from underpopulation. The poor cell is all alone and doesn't survive. A live cell with more than 3 live neighbors dies. The poor cell is now too crowded and dies from overpopulation. But cells can also reproduce. A dead cell with exactly 3 live neighbors is born, it becomes a live cell. And as a consequence of these 3 rules, a live cell with 2 or 3 live neighbors survives to the next turn. And that's it. Those are all the rules. All we have to do is define an initial configuration of live cells, hit play, and then sit back and let the simulation run, applying these rules over and over and over again. And here's the incredible part. From this simple set of rules, astonishingly complex patterns begin to emerge, patterns that no one programmed. Some of them seem to move across the grid, like the famous glider. Of course, that movement is an illusion. In reality, it's simply cells dying and being born in a sequence that creates the effect of movement across the grid. Other patterns seem to oscillate, like the blinker. It's as if periodic behavior appears out of nowhere. And if we let the simulation run for even longer, even more complex machines emerge. Patterns like guns that periodically shoot out gliders, or even logic gates and, or, not, and eventually complete computers. The fact that this simple system is Turing complete, meaning it can simulate any computer algorithm, is the ultimate emergent property. And that word, emergence, is the key to understanding the magic of the game of life. An emergent property is a feature of a system that is not found in its individual components, but rather arises from the interaction between them. The classic example is the wetness of water. A single H2O molecule by itself is not wet. Wetness is a property that emerges when billions of water molecules interact with each other. The truly wonderful thing about the game of life is that it shows how new complex properties can emerge in a universe from a very simple set of rules, just like, perhaps, our own.